This flow control structure works because natural gravity drives water flow. The clever bit here is operating completely without mechanical power. Passive flow control devices alter water movement inside drainage channels, natural streams, and subterranean pipe networks completely automatically. By positioning static geometric barriers across watercourses, these engineering structures adjust fluid impact based entirely on available water volume. Devices like overflow weirs and specialized flow splitters continuously respond to changing rainfall rates without requiring human intervention or electrical sensors. Civil engineers have utilized these fundamental passive principles for thousands of years to sustain agricultural irrigation and protect urban settlements from flooding. However, simply constructing static diversion channels to route raw river water creates a severe unforeseen engineering challenge that early hydraulic builders quickly encountered. As natural stream water flows across land, it carries massive volumes of suspended silt, heavy sand, and mineral debris scoured from upstream riverbeds. When diverted river water enters lower velocity irrigation canals, heavy sediment rapidly drops out of suspension, causing severe silt buildup along the canal floor. Early engineers initially assumed widening irrigation channels would clear sediment, but reduced fluid velocity actually accelerated silt deposition, causing complete channel blockages. Without a reliable physical mechanism to handle continuous sediment accumulation, passive diversion systems regularly clogged and failed during seasonal agricultural cycles. Ancient Chinese engineers solved this critical setback over 2,000 years ago by developing a counterintuitive flow control structure that works with sedimentation. Rather than trying to stop silt from settling, they engineered specialized low-velocity drop basins designed specifically to force heavy sediment deposition in precise locations. By intentionally depositing silt into pre-planned settlement areas, the main downstream irrigation channels remained completely clear of choking debris and flow blockages. This counterintuitive mechanism maintained continuous water delivery to agricultural fields while isolating heavy sediment accumulation inside accessible catchment basins for easy removal. Preserving long-term channel performance required essential yearly maintenance, where workers manually cleared accumulated silt from designated drop zones during low water seasons. The bigger problem was managing extreme seasonal flow variability, where systems had to handle minimal drought trickles and destructive flood surges simultaneously. During dry summer months, thin river streams lacked sufficient hydraulic depth to spill over natural banks into elevated agricultural feeder canal intakes.
Conversely, massive flood surges entering steep spillways gained immense kinetic energy, scouring downstream riverbeds, destroying masonry dams, and eroding surrounding bank infrastructure. Designing a single passive structure capable of capturing low-volume flows while safely dissipating the violent kinetic energy of massive floods appeared virtually impossible. Engineers had to develop sophisticated physical geometries that dynamically alter hydraulic resistance based entirely on the total volume of incoming water. To solve low-flow capture in agricultural regions like Hawaii, civil engineers constructed simple low dams positioned directly across shallow, wide stream channels. Instead of damming the river entirely, these low barriers force the entire volume of a shallow stream toward one designated side of the riverbed. By squeezing the shallow stream into a narrow channel path, local water depth increases significantly, elevating the fluid level without relying on mechanical pumps. This elevated local water height keeps agricultural irrigation canals completely full and operational, even when overall stream discharge drops to exceptionally low levels. When heavy seasonal rains cause feeder canals to become overfull, integrated passive spillways automatically dump excess water back into primary stream channels. This self-regulating overflow loop prevents crop fields from drowning during heavy storms while maintaining optimal, consistent water levels inside working irrigation canals. To solve the opposite extreme, high-energy overflow descending steep dam spillways, engineers implement energy-dissipating structures using a series of heavy concrete piers. These massive concrete piers are installed along the spillway floor apron to directly intercept fast-moving water rushing down steep concrete slopes. As high-velocity water collides with the concrete piers, violent hydraulic turbulence converts destructive kinetic energy into harmless spray and internal fluid friction. By significantly slowing down the descending water, concrete piers prevent catastrophic erosion and structural undermining at the toe of the spillway slope. In modern subterranean infrastructure, proprietary flow splitters use these exact passive principles to manage stormwater runoff and combine sewer overflow networks. During intense rain events, internal weir geometries passively divide incoming storm flow between municipal wastewater treatment facilities and overflow storage basins. Because these passive flow splitters contain zero motorized valves or electrical sensors, system reliability remains exceptionally high during severe weather grid outages. Engineers evaluate these passive hydraulic devices strictly at documentary level, recognizing that performance depends entirely on precise physical sizing and static contours.
Furthermore, operational safety requires adhering to design limits, including mandatory periodic maintenance to clear accumulated sediment and debris from internal channels. By relying on fundamental fluid mechanics rather than complex active controls, passive flow structures transform unpredictable natural waterways into controllable civil assets. Carefully calculated concrete profiles, stone barriers, and channel geometries convert gravitational energy and fluid momentum into predictable, self-regulating hydraulic control. Flow control structures demonstrate how passive physical design can master complex fluid dynamics, providing reliable water management across thousands of years of engineering history. From ancient Chinese sediment drop basins to Hawaiian canal diversions and modern spillway piers, static geometry efficiently replaces expensive powered machinery. By converting fluid friction, channel width, and gravity into control mechanisms, engineers safely divert, calm, and store water without consuming external energy. Understanding these counterintuitive passive mechanisms highlights the lasting elegance of hydraulic engineering, designed in complete harmony with natural physical laws. Through clever passive geometry and essential routine maintenance, flow control structures manage vital water resources reliably and safely for civil infrastructure worldwide.